So we're going to continue on with our 10.1 notes. All right, so we left off when we had two equations. So the first one was a growth equation, and the second one was a decay equation. All right, so this one says in 2006, about 1 billion people used the internet. The number increases by about 19.5% each year. Write an exponential growth equation to model that situation. So the equation that we talked about for exponential growth was a of t equals p times 1 plus r raised to the t. Okay, p is called the principal amount or the initial amount, r is your rate, t is your time. So whenever it says write an exponential growth equation or something like that, function, that means t is still going to be in your answer. So we're going to have our amount after time t. We started with 1 billion, so 9 zeros. We have 1 plus, my rate is 19.5, so 0.195. Remember, you could move it over 2 places to get that. Raised to the t. So the function that works for any time t is 1 billion times 1.195 raised to the t. So I could plug in any time value, and I would get the answer for that number of years. Okay, so that's what part B asks. It says, how many people will be using the internet in 2012? Okay, do I plug in 2012? No. 6, because I told you originally it was 2006 when it was that 1 billion people. So this is 6 years later. So t equals 6. So we're going to say a of 6 equals 1 billion, 1.195 to the 6. Now, if you're lazy, you could do 1 times 1.195 to the 6, knowing that this is going to be in billions of people. But at the end, you need to remember to write that. Like you'd say, 2 point blah, blah, blah billion people. Okay. So when we do this, we get, remember you have to follow your order of operations. So the order of operations is please excuse my dear Aunt Sally. So we have to take care of the exponent part first before we multiply by 1 billion. So I get 1.195 raised to the 6th. So when I do that, I get 2.912. Now, a lot of you guys will be tempted to write 1 billion times 2.912, and then you use this rounded answer. Don't use the rounded answer. Leave that number in your calculator, and now multiply by 1 billion. So when you do that, you get 2,912,107,693. So 2,912,107,693. My units in this case, it's not dollars like that last example, it's people. Okay, so that's our answer. Okay, this one's a little bit different. So it says the pressure of Earth's atmosphere is 14.7 pounds per square inch. That's at sea level. Now for each mile that you go up, the pressure decreases by about 20% for each mile of altitude up to about 50 miles. Okay. So write an equation to describe the situation. So our pressure is decreasing. So we're going to use the decay equation, which is P times 1 minus R to the T. Okay. And the first class had trouble understanding this, so let's think about it. So if I'm at sea level, my pressure is 14.7. Okay, 1 mile up, my pressure is going to decrease by about 20%. Okay, so if I'm going to the store and I see something's 20% off, I don't think of 20% and then subtracting from that price. What I do in my head is I say, oh, I'm going to pay for 80% of the price. Does that make sense? Do you guys do that too? All right, so what you're doing is you're taking that number you had, 14.7, and you're multiplying by 80%, or 0.8. 2 miles, you do it again. You do 0.8 times 0.8 times 14.7. So it's 0.8 squared. So t miles up would be 0.8 to the t times 14.7. Okay, that's where this equation is coming from. P is your 14.7, your original pressure. your rate is 1 minus 0.20. That's how you got the 80%, 0.8, or 1 minus 0.2, you could write. And t, we don't know. Okay, so a of t equals 14.7 times 0.8 to the t. Mm-mm. So what would the atmospheric pressure be 20 miles up? So that'd be 20 is your t, so t is number of miles in this case. Okay, so 14.7 times 0.8 to the 20. So you have to do 0.8 to the 20 first. So when I get that, I get, so if I was writing like notes, so I'm writing myself some little notes for doing this problem, I'd probably write this. Okay, but the number in my calculator is 0.011529215, and I'm sure it goes on past that. Okay, so keep that number in your calculator and now multiply by 14.7. So you get 0.169 pounds per square inch. I usually round to 3 decimal places because that's what you guys will have to do in AP Calc. So 3 decimal places at the very end. Okay, and that's your answer. Okay, things to remember. Like in number 3b, this was our amount after 6 years, a of 6. We did not divide by 6. Remember we talked about that last time? That's like a function. It's like f of 6. We leave it like that. Your amount after 6 years is 2 million something people. Okay, so let's go ahead and skip to 10.2. Sam, you with me? So like I was saying, Algebra 2 second semester is a lot harder because it's all new things. So when you guys see this, you're like, ooh, log. I've seen that button on my calculator, but I don't know what it is. So it's all new. So this starts out pretty easy. It does get a little bit harder. But if you guys stay up with your homework and go to math help and all that, you should be fine. This won't be bad. All right, so it says, suppose you want to know how to find suppose you want to know how many times you have to multiply 2 by itself to get 8192. So let's say I had something like that. What I'm trying to solve is 2 to some power equals 8192. Okay. We've never done that before, where we've had our variable as an exponent. We've never seen that. Okay. Logarithms are what allow us to drop the exponent. They allow us to solve for x. Okay, so the way you would do this now, we don't know anything about logarithms. So you guys would just keep doing 2 times 2 times 2 times 2 on your calculator, right, until you get the answer. Or you do like 2 to the 5th, get an answer, 2 to the 6th, try again, 2 to the 7th, try again, you know. So you would have to keep doing that in order to find the answer. Okay, we don't want to have to do that. This only would work for like a whole number of times. What if it was 2 to the 8.5? That would be a different situation. We wouldn't know how to solve that. So we would need logarithms. Okay, so a logarithm is the exponent to which a specific base is raised to obtain a given value. So very confusing definition. Basically, the most basic thing you need to know is how to switch from exponential to log form. If you do not know this, you will fail the test. We do this all the time. Okay, so exponential equation is going to look something like b to the x equals y. The logarithmic equation is going to be log base b of y equals x. Now b is a subscript in this case, log little b of y. So let me write it real carefully. Log subscript b of y. Y is not an exponent. It's on the same level as log. It's written in the same size of font equals x. Now, the way I had to memorize this when I was in school, I had to remember how to switch back and forth, which you guys, like I said, you'll have to know. So I always remember the base of the exponent is the same as the base of the logarithm. The little b is the same as the base of the exponent. Okay, and then I did a little hand gesture. So do you guys see my hand? So I'm going to start with the b. I'm going to skip over the equal sign and go to the x and go back to the y. So it's going to be b to the x equals what's left, y. Does that make sense? So it's going to be b to the x equals y. Okay, so that's how we switch it back to this exponential equation. All right, so if I have log base a of x equals y, my base of my logarithm is the base of the exponent, so it's a. So it's a to the y equals what's left, x. So a to the y equals x. See how it works? Okay, so it was pretty easy for me when I switched from log form to exponential form. What got tricky when I was in school was switching from exponential form back to log form. So that's like this next example. So if I have 2 to the third power equals x, that's going to be log base, what's the little number? 2. What's next to it? X equals 3. Yep, 2 to the 3 equals x. All right, try the next one. So it's a to the y equals what's left, the a to the x. Okay, if I had a to the y equals a to the x, what would that then mean?
X is equal to y.
Yeah, x is equal to y. So that's going to be a theorem that we're going to learn later. If I have log base a of a, it's like they cancel each other out, and you just are left with the x. Now the x is up as an exponent, which is going to be really strange. It's now all of a sudden going to drop down, so we'll talk about that. All right, so this next one, if I have log, it's going to be log base 4 of x equals negative 2. So does everybody see how to switch from log to exponential? So it's very important in this chapter. When all else fails, do that. All right, so 5a. So I have log base 10 of x equals 3. So when you guys see that, it's kind of making you panic because you have an equation that has logarithms, and you're like, well, what am I supposed to do? All right, switch to exponential then. So if we switch to exponential form, it's 10 to the third equals x. What is 10 to the third? 1,000. All of you guys should be able to do this in your head. You should have all learned this trick in school where if you had 10 times 10, it's 100, a 1 with 2 zeros. 10 times 10 times 10 is 1,000, a 1 with 3 zeros. 10 to the fourth is 10,000, 4 zeros, right? Have you all seen that trick? I feel like my elementary school is very different than your elementary school. We had to know, like, the multiplication tables and memorize those. Did you guys memorize your 12 by 12 tables? Yeah? I feel like some people didn't because I'm always like, what's 4 times 9? And they're like, ooh. So, yeah, you should know those things. All right, so 10 to the third is 1,000. So your answer is 1,000 equals x. All right, so how about this one? So I have log base 16 of x equals 12. So that's 16 to the 1/2 equals x. What does that mean to have 16 to the 1/2 power? Square root. So it means that square root is there. So square root of 16 equals x. The square root of 16 is 4.
Why isn't it plus or minus?
Good question. Can anybody explain why it's not plus or minus 4?
Because like the 1/2 is already principal.
Yep, it's the 1/2 means there's a square root that's already there. If the square root is already there, then that means that it's the positive root. All right, if I was solving and I had x squared equals 16 and I was solving an equation where I was the one that took the square root, so I took the square root of both sides, then you have to write plus or minus. All right, but in this case, the square root's already there. Okay, we also will talk more about logarithms, and you'll see that you can't take a log of a negative number, so we'll get to that eventually. All right, common logarithm. So all of you guys look at your calculators now. Do you guys see the log button? Yeah, the log button is the common logarithm. Okay, so your calculator only does base 10. So when you see log, that is log base 10. It will also do base e, which we call natural log ln. But we will get to that later on in the chapter. So we don't know how to do anything else on our calculator besides base 10. Okay, so that's called the common logarithm. So it says if no base is written, we assume it's base 10. All right, so I have log of 1. So there's no little tiny subscript number. So no base is written. So what that means is log base 10 of 1. Now you guys can do that on your calculator. Go ahead and do log of 1. What do you get? 0. But I said evaluate using mental math. So we need to know how to do this without our calculator. And you will have a non-calculator portion of this test too. No, it's terrible. All right, so let's think about how to do this without a calculator. Yeah, same thing as before. If I have log base 10 of 1 equals some number, we'll call it x. How do I switch forms? 10 to the x equals 1. So 10 raised to some power equals 1. What does that power have to be? 0, right? Anything to the 0 power is 1, except for 0. 0 to the 0, we don't know. All right, so x equals 0. So let's do the same thing here. So we're going to say equals x. You can draw in your little 10 if you need to see it. So log base 10 of 10,000 equals x. So we have 10 raised to the x equals 10,000. So what's x? 4.
Oh, wait.
4 zeros.
Yeah.
So what's this one going to be? 3. 3 zeros. Okay, this gets a little bit harder. So if I have log base 5 of 3125. All right, so that's 5 to some power equals 3125. So I said without a calculator, so let's think through this. So let's try some different things. 5 to the first we know is 5. 5 squared is 25. 5 fives. 5 cubed would be 5 25s. So what's 5 25s? 125. 5 to the fourth would be 5 of the 125s. So if I had 125 and I added it to itself 5 times, 625. Okay, 5 to the fifth would be 625 5 times. So it's like 600 5 times would be 3,000. 25 5 times would be 125. 3,000 plus 125 is 3125. All right, so it's 5 to the 5, so x equals 5. All right, log base 15 of 1. Because it's 15 to the x equals 1, so x has to be 0. 15 to the 0 power is what gives 1. All right, so with this one and this one, can you guys kind of do it like a theorem there? Log base anything, right, of 1 equals 0. So log base b of 1 is always going to be 0. All right, and then this last one, so this is 4 to the x equals 256. I saw Naveen bust out his calculator. Good mental math skills there. He says it's 4, so you can go through that same process. 4 to the 1, 4 squared. 4 to the third is 64. 4 to the 4 is 256. So x is 4. He says he guessed it. He just checked. All right, next up. All right, so special properties of logarithms. So these ones we've kind of talked about along the way. So the first one, if I had b to the 1 equals b, if I see that in log form, it's going to look like log base b of b equals 1. Same thing, b to the 1 equals b, right? So basically, if you see like log base 7 of 7, you should immediately know that the answer is 1, because you're thinking 7 to some power equals 7, that power has to be 1. See how it works? It's kind of like these cancel each other out. You know how like multiplication and division undo each other? Log base 7 of 7 undoes each other. You get 1. All right. So if I have log base b of 1 equals 0, exponential form is b to the 0 equals 1. So basically, that's the one we were talking about. If I have log base anything, so 2,157 is my base of 1, it has to be 0. Because 2157 raised to what power makes 1? 0. See how it works? So these are 2 important things that you need to know. I would start making flashcards for the logarithm properties because we're going to have a lot of them. So make flashcards for your test. It will make your life a lot easier. All right.
Oh my gosh.
Yeah. Should flip to the next section.
Yeah.
So logarithmic function. So a logarithmic function is a function of the form y equals log base b of x. Okay, do you guys remember back in chapter 7 when we found the inverse of a function? Yeah, how did we find the inverse of a function?
Change x to y.
You changed x, you exchanged them like x and y, switched, right? You switch your x and y values. All right, same thing when you graphed it. You just had a point, like if you had 2, 4, you had 4, 2 on your inverse function. All right, so you switched them. Casey, you with me?
Yeah.
All right, so if we're going to switch them, how do I write my exponential form for y equals log base b of x, first of all? So what's exponential form for that? y equals log base b of x would be b to
e
the
to the
y equals x. So that means its inverse function is b to the x equals y. Okay, so you switch x and y for the inverse. Okay, so what this means is you have this graph. Remember, inverse functions always reflect across the line y equals x. So this first function that we have graphed in is what we learned last time, like basically like y equals 2 to the x, something like that. It goes through the point 0, 1. So it's some number to the x. Okay, its inverse function has to have all of the opposite points. So instead of having 0, 1, it's going to have 1, 0. So log functions are going to go through 1, 0. And notice over here, as my x values become negative, they get really close to y equals 0. So as my x values get really close to x equals 0, my y values become more and more negative. That's what's happening there. See how it's working? That's why it's a reflection across the line, y equals x. Okay, so log functions are going to look like that.
What do we call that line?
That line is y equals log base b of x. Okay, now the important thing about this graph of a log function, notice its domain. Domain is all the x values that we have graphed. It's what?
Oh wait, are you only on the second one?
Yeah, only on this one.
Oh, it doesn't go in any negative.
Yeah, we have no negative x values. We don't even have when x is equal to 0, right? It doesn't cross that axis. So can't take the log of a negative number or 0. So let's try it. On your calculator, try like the log of negative 10. Hit enter. What do you get?
1 plus something.
One
You have your
plus
set, so it's-
1.36.
What?
1 plus 1.79.
You guys have your set so that you have eyes. You don't get a real answer. When I do it, it says my mode is set, so I have real numbers only, not a plus bi. So when I hit enter, it says non-real answer, error.
Yes.
Is that what you guys have? All right, try log of 0. It says error, domain. So you're getting errors. It's not working. Okay, so you cannot take the log of a negative number or 0. It doesn't work. All right, so explain why log base 0 of 3 and log base 1 of 3 do not exist. Okay, so let's set them equal to x and solve. If I switch to exponential form, this first one becomes 0 to the x equals 3. 0 to any x value, I mean 0 to the 0 we don't know, but any other x value is 0, right? 0 equals 3. Doesn't work. Same thing here, 1 to the x equals 3. 1 to any value is 1. 1 equals 3. Doesn't work. So this is why these are not possible. So I can't do log base 0 or log base 1.
You can do fractions in between.
Yep. All right, number 2. So use the given x values to graph each function. So let's say we have f of x equals 3 to the x. So if I have 3 to the negative 2, remember that's 1 over 3 to the positive 2. So it's 1/9. Okay, so I'm going to have the point negative 2, 1/9. So a little bit above the axis. Okay, if I plug in negative 1, I have 3 to the negative 1. Remember that's 1 over 3 to the positive 1, which is 1/3. So I have negative 1, 1/3, so a little bit higher. The next one I have 3 to the 0. 3 to the 0 is 1. Three to the 1 is 3. 3 squared is 9. So I have 0, 1, 1, 3, 2, 9. Oops. Okay, you end up with this. We talked about this before. This is y equals 3 to the x, kind of like y equals 2 to the x that we graphed before. Okay, so graph its inverse. So that means every point we have, we want to switch the x and y values. So instead of having negative 2, 1/9, I'm going to have 1/9, negative 2. So like right there. Instead of having negative 1, 1/3, I'm going to have 1/3, negative 1. 0, 1 is going to become 1, 0. 1, 3 is now going to be 3, 1. And we're going to have 2, 9 as well. So way out there. So you end up with that. Notice how it's a reflection across the line y equals x. Okay. That function is going to be y equals log base 3 of x. And the reason is because, remember, if you switch this one to log form, it's log base 3 of y equals x. We're switching the x and y values. So we have y equals log base 3 of x instead. Do you see how their domain and range are related? So the domain of the first one is all x values, so negative infinity to infinity. Our range for the first one is everything greater than 0, so 0 to infinity. They switch for the second one, so our domain for the second one is all the x values we have on our graph, so 0 to infinity. Our range is all the y values we have on our graph, and this does go up forever and ever. There's no like horizontal asymptote there. So it's negative infinity to infinity. Okay, let's look at pH really quickly. All right, have you guys all talked about pH before?
Yes.
You guys know what pH is? Okay. So pH is basically a way to measure the acidity of a substance. So we talk about something being a base or an acid, right? So if something's really high on the pH scale, so the closer to 14 it is, the more basic it is. The smaller the number is, the closer to 0 it is, the more acidic it is. So think of like really, really acidic things. I don't know.
Battery acid.
Lemon juice, sulfuric acid.
Battery acid.
Yeah, battery acid probably. Yeah, so think of really basic things like milk would be basic. I think like liquid plumber, like that kind of stuff. Is that basic? I don't remember. I haven't done that one. It's acidic?
Yeah.
I can't remember. There's something you put down your pipes there. Sodium hydroxide. Busting out all the chemistry ones. All right, so basically there's an equation where it's pH equals negative log of H plus. So H plus is called the hydrogen ion concentration. Okay, so I was given the hydrogen ion concentration. It always has brackets around it too, like H plus with brackets around it. Is this number, 0.00794. So write a logarithmic equation for the pH of the solvent. So pH is going to be negative log of 0.00794. Okay, what base is that? 10. It's not written, so it's automatically base 10. So our calculator will automatically do that for us. We just do log of 0.00794. We have a negative out front, so do opposite of the answer. You guys get 2.100, right? So about 2.1. That's the pH. So is this a base or an acid? Acid. So things that are less than 7 are acidic. Okay, so let's do this one really quick. So do number 2 really quick. You're just plugging into the formula. You can actually do negative log of the number all in one, like all on your. So here we have pH equals negative log of 0.00014. When you do that, you get, we'll round to 2 decimal places, so 3.85. So what is that? Orange juice. So do the other ones. I got 2.09 for the next one. So lemon juice. And what'd you guys get for the last one? Yeah, you can do it all in one, like all on your calculator, negative, log, or whatever. Okay, so 3.13, so that's grapefruit, barely, right? Okay, and then the very last problem talks about hydrangeas. Okay, so the flower color of a big leaf hydrangea is determined by the soil pH. So a gardener is growing blue hydrangeas, and she believes lime may be leaching out of a nearby sidewalk, increasing the pH of the soil, so making it more basic. The gardener measures the hydrogen ion concentration and finds it to be 0.0008 moles per liter. If it's between 5 and 5.5, she'll get a blue one. If it's between 5.5 and 6, she'll get a purple. If it's between 6 and 6.5, she'll get a pink. So will she get the blue hydrangea she's trying to grow? So gardeners actually add acidic, like they add acidicity, is that what you said? How do you say that? To the soil, or they add some base things to the soil to change the color of their flowers. 1, 2, 3, 4, 5, 6. So what do you get? What's 6.2 what? 6.22? So it's between 6 and 6.5, so she's getting a pink hydrangea. So no, she's not getting the blue one. Okay, so she would need to add something to the soil to make it more of an acid.